and want to hand over to you, Peter, for your talk. Thanks a lot in advance. The floor is yours.
Thank you very much, Robert, and thank you for the kind introduction. So in this talk, I will give you an introduction to combining model and deep learning based approaches for thermal NDA. Before I would go into the details, let me tell a few words about the background of this research. As it was mentioned already by Robert, today I will present the results of a joint cooperation. Since in 2019, I was a postdoc at Mario Suemeyer Institute at the JKU, and he initiated a really big cooperation between 4 institutes. So we started to cooperate with Bernard Lehne from Silicon OCR Labs. He's a machine learning expert. We also cooperated with Günther Meyer and Gregor Tümerer from the FH Wales, and also with Peter Bukurtsev from the RECENDT. So today I will present the results of this joint research, in which the focus was to improve the the accuracy of the thermographic imaging techniques, where the goal is to analyze and detect the structural imperfections of materials. Of course, you know that better than me. This could be done by using many methodologies, ultrasounds, electromagnetism, or thermography. In thermography, we are heating up the investigated object, and based on the temperature evolution in time that we can measure on the surface, we need to reconstruct the internal structure of the specimen. At the bottom figure, you can see an example, a simulated 2D example, where the horizontal axis represents the depth and the vertical axis represents the surface. And we placed 3-point defects into the material with increasing depths. And if we start to simulate the heating of this 2D specimen, we can measure the temperature evolution in time on the surface, which results in an image that you can see in the middle. So during the reconstruction, the only thing we have is the images, the surface temperature images that you can see in the middle. And out of that, we need to approximate the initial temperature profile of the specimen. On the right side, you can see an approximation to the ground truth initial temperature profile. And you can notice that defects close to the surface could be easier to reconstruct with a higher accuracy, but as we go deeper inside the material, the accuracy degrades, and also artifacts appears on the reconstructed image. So the goal of the research was to increase the accuracy even for deeper deep defects and reduce the artifacts on these images. Mathematically, this can be formulated as a linear inverse problem, where which could be defined by a system of linear equations that you can see in the middle. So in this system, phi is a matrix that represents the heat conduction process. And on the right side, the T measure is a vector or a matrix that includes all the surface temperature measurements. And during the reconstruction, the goal is to retrieve the initial temperature distribution that is denoted here by X init. There are many challenges during the reconstructions. From numerical point of view, this is a discrete ill-posed inverse problem. So the condition number of the phi matrix is very high, and there is no clear gap between the single values to make the matrix well conditioned. Computational point of view, the size of the matrix, so the rows and the columns, are proportional to the number of pixels on the surface temperature images, which could be hundreds of thousands number of pixels, so it's very large. And also, it's also not straightforward how we can derive the phi matrix in the equation. So it is just an approximation to what is happening in the real world. In order to improve the reconstruction, several heuristics can be utilized, like non-negativity, since we are working with the temperature data. Also, sparsity could be used, since in the reconstructed image, non-zero pixel values are representing either noise or defects. And also group sparsity could be utilized, because non-zero pixel values, which are grouped together, are most likely to be defects instead of noise. In this slide, I just want to briefly refer back to Peter Buchwitzer presentation in July. He introduced with Maya Günther two-stage reconstruction process in 2017, where the photothermal problem, the photothermal reconstruction problem, were converted to a photoacoustic reconstruction problem. So instead of working with the surface temperature data that you can see in the middle, by using a linear transformation, we convert the data to another domain. This is called a virtual wave domain. And then we can apply reconstruction techniques used in photoacoustics. The main advantage of the method is that it takes into account the lateral and the axial heat flows, and it also allows to use photothermal tomographic methods. So this is the basis of the talk today. However, in each of the stages, in the two-stage reconstruction process, we have different challenges. So in the first stage, both stages can be described by a system of linear equations. And in the first stage, the matrix K is explicitly formed, but it still defines an ill-posed inverse problem. So regularization is necessary. Estimating the right amount of regularization is not straightforward. And also formalizing and including the heuristics that I showed you at the beginning. So including these heuristics into the reconstruction process is not easy, because we need to formalize these constraints and penalties mathematically. So these are the challenges in the first stage. And in the second stage, we have again an ill-posed inverse problem, which is in addition to the first stage, it is also large scale. So the matrix here that describes the system of linear equation is much bigger, or it cannot be explicitly formed. And yeah, we still need regularization to get a meaningful solution. Okay, and now I will show some possibilities how to make the reconstruction in each stage. So the title of the presentation was Combining Model and Deep Learning based algorithms. And now I will start with the model based approaches to make the reconstruction in the first and in the second stage. So in stage one, we can formulate the reconstruction process in two different ways. The formulations are coming from image processing. In image processing, we can do sparse signal recovery by using a synthesis model or the analysis model approach. The two approaches differs from each other in a way how they assume sparsity of the solution. So in the first stage, we want to determine the virtual wave image. So in both stages, the goal is to find a good approximation to the virtual wave image. And in the synthesis model, we can look for the virtual wave image in a linear form, and we can assume the sparsity of C. In the second approach in the analysis model, we are looking for the solution X word, but we assume the sparsity of X word in another domain. So in the penalty term, in the L1 penalty term that forces the sparsity of the solution, we are assuming sparsity in another domain. The main advantages of the first stage is that K is well defined and it's small compared to the number of pixels or measurements made on the surface. And yeah, K is explicitly defined. So if I go back to this slide, you can see K. For K, we have a very compact formula. The matrix, each element of the matrix can be easily computed. And the transformation in each column can be done in parallel. So these are the main advantages of the first stage. And due to the size, the smaller size of the K matrix, we can also perform single value decomposition and estimate the optimal value of the regularization parameter. So here you can see lambda, which controls the trade-off between under and over regularization. And the value of lambda should be provided by the user. So the value of lambda depends heavily on the estimated noise level on the in the measurements, but the determining the optimal value of lambda is also depending on the user. But for that, we can use some automatic built-in methods, the L-curve method, cross-validation, normalized correlative periodogram, which can be calculated easily due to the smaller size of the K matrix. Here you can see some examples for the two approaches, for the analysis and the synthesis approaches. In the middle, you can see the virtual wave image that corresponding to the image with the 3-point defects. And you can see this image is sparse, but not too much, not very sparse, because less than or approximately 50% of the image pixels on this image are non-zero. So by introducing some transformation by using the synthesis and analysis methods, we can increase the sparsity. So if we transform the virtual waves into the Abel domain by using the Abel transformation, then we can increase the sparsity. So the number of non-zero pixels on this image is reduced to 1/3 of the overall number of pixels. And also we can use the non-negativity constraint here. So if we looking for the solution in the Abel domain, not just sparsity, but non-negativity of the values C can be utilized. In addition to that, we can also apply the analysis approach by transforming the virtual waves into the curvelet domain. Curvelets are extensions or generalizations of the wavelet transformations, where the spectrum is localized not just in frequency and so not just parameterized by the localization and the frequency, but also by the orientation. And curvelets are very well suited to represent images, for instance, seismic images or acoustic images in a compact, very compact form. So this is why we thought, since the virtual waves are obeying to the acoustic wave equations instead of the heat equations, we thought the curvelet domain could be also suitable for representing the virtual waves in a compact form. And this is true, since if we transform the virtual waves to the curvelet domain, then the number of non-zero image pixels are heavily decreased, so only 14% of the overall number of pixels are non-zero. And if we take a noisy virtual wave image, and in the curvelet domain we use only the 1% of the overall number of curved coefficients and take the inverse curved transformation, then we can get we can still get back the main characteristics of the virtual waves. We have some artifacts, but still the virtual waves are visible on the image by using only 1% of the overall number of curved coefficients. Although in terms of the mean square error, we did some experiments in 2020 in this paper, and it turned out the sparsity plus non-negativity is a stronger assumption than the increased sparsity in the curved domain, because by using the Abel transformation and utilizing also non-negativity, we could get better reconstruction accuracy in at various noise levels. But I would say in the future, if we use machine learning techniques, I think these two transformations could be combined in order to further improve the reconstruction process in the first stage. Okay, so that was what I want to say about the model-based approaches in the first stage. And let me jump to the second stage, where the task is to solve a system of linear equations like this. So on the right side, we have the virtual waves, or the approximation to the virtual waves that we got from the first stage. We have an M matrix that describes the wave propagation, and X in it is the initial temperature distribution that we are looking for. In this case, M is much larger than we had in the previous stage. It cannot be explicitly formed. And the problem here is that we also have to take care about the distortions that was introduced by stage 1. So here you can see an example to the approximation of the virtual wave images. So this was the ground truth virtual waves. We don't know that. We can simply approximate it during the first stage, and the approximation would look like this. Obviously, this is not perfect, especially deeper inside the specimen. And these nonlinear distortion that was introduced by the first stage, the first reconstruction in the first stage, should be also treated in the second stage. In the second stage, we could also utilize the group sparsity assumption. The group sparsity means that the image is not just sparsed, but the non-zero image pixels are close together. But for model-based group sparsity approaches, we need to provide the size and shape of the groups. And in non-destructive testing, actually, we are looking for the goal is to determine the size and the shape of the defects. So we don't know this information, and because of that, we cannot utilize this assumption. On this image, I place the defects in such a way that they fit into the rectangles that I a priori defined, but in a normal setup where we don't know the positions of the defects, this could not work. Okay, so I told you the challenges in the second stage. So we cannot utilize group sparsity. We have nonlinear distortion coming from the first stage. The matrix M is much larger. So instead of applying some model-based approaches, we will apply machine learning algorithms to make the reconstruction in the second stage. In cooperation with the Silicon Austria labs, we initiated a project in 2019 where our goal was to train neural networks for solving this optimization problem. So for a certain a priori given phi matrix, and for a set of measurement matrices or vectors, train the network to provide the solution of this optimization problem. So this optimization problem is something that we use to describe the reconstruction process in the first and in the second stage. But in the second stage, we could not apply numerical model-based approaches due to the challenges that I listed before. So the potential benefits of applying model-based approaches in the second stage could be more accurate final solution, so better local optimum, and also the efficiency, less computation time. So at this point, you can ask, okay, why I'm speaking about less computation time, since we know training neural networks are very difficult. Yeah, that's true. So training, especially very deep neural networks, is really computationally intensive or resource intensive method. But the good news is that the main computational load is shifted to this offline training process. So doing the inference, so once the network is trained and applying it on a certain reconstruction setup is very fast. So even real-time reconstruction would be possible if the network is already trained. So these would be the benefits to apply such algorithms. Okay, so in order to check our assumptions and how we could apply these machine learning algorithms, we defined two setups. The first setup utilizes the two-stage reconstruction introduced by Peter and Günther Meyer. In the first stage, we extract the virtual wave images by some model-based approaches. And in the second stage, we train the neural network on the images we extracted in the first stage and on some target images. And the reconstruction in the second stage would be performed by a machine learning method. So this first setup is called a hybrid approach. And in order to compare its efficiency, we also define the second machine learning setup where we do not utilize the two-stage reconstruction. We just go from the measurement vectors to the initial temperature distribution. So this is called the end-to-end machine learning approach. Okay, so I already defined the two machine learning setups. In all of these setups, we are working on 2D images. And in order to get a 3D reconstruction of a 3D material, we would perform the reconstruction in each cross-section of the investigated specimen, and then we merge the cross-sections and construct the 3D structure of the investigated object. What kind of network architectures we used? So we used UNet. UNet is a special network architecture that was specially made for segmenting medical images where the training data is limited. Actually, we have the same problem here. So in medical image segmentation, in order to train a network, we need a lot of data. And for doing this in a supervised manner, we need the data and its segmented version. And the segmentation should be made, the annotation should be made by involving medical experts, and it should be made by hand. So it takes a lot of time. So preparing the data set on which we perform the training takes a lot of time, human effort, and it's costly. This would be the same. We would have the same drawbacks in case of thermography, because in this case, we should make physical phantoms where the defects, positions, shapes of the defects are predefined. So we could make a lot of training data based on that specimens, and then we can perform the training. So, but making such a lot of physical phantoms where the defects, shapes, and positions are known a priori is also costly. So we have limited amount of data here as well, and this is why we selected the UNet, which can handle this problem. The UNet has two branches, an encoding and a decoding path, where during the encoding path, the dimension of the input image is reduced, and from a bottleneck layer, the dimension of the latent space is increased to reach the dimension of the target image. In our specific case, the input to this neural network were either the surface temperature data or the virtual waves or the approximated virtual waves, and the output should be a binary image indicating the defects by non-zero image pixels. Okay, but how we can generate training data for the network? So after having discussion with Peter and with Maya Günther, we decided to consider the heat diffusion equation and solve it for adiabatic boundary conditions. In this special case, the differential equation has an exact solution, which can be simply defined by this formula. T hat and T0 hat denotes the Fourier transform of the surface and the initial temperature profiles. So if we just provide a binary image, taking its Fourier transform, multiplying it with this exponential and Fourier transforming back, we can simulate the surface temperature images. So we can generate as many images with as many defects as we want. So this is how we generated 3,000 noise-free surface temperature images, where we placed 2 to 5 square-shaped defects inside the 2D images. And we also added Gaussian noise between the SNR ranges from -20 dB to 70 dB. And also generated, with the same process, we generated 1,000 number of samples for testing the network. Here you can see an example. On the top left corner, you can see the target mask or the target image, where the black squares representing the defects. So this is what we should estimate. On the top right corner, you can see a strictly model-based approach where we use the virtual wave reconstruction in the first stage and FSAFT reconstruction in the second stage. And you can see some of the defects are merged together, and also the deeper ones cannot be seen. And the bottom two figures, the bottom two lines, you can see the end-to-end and the hybrid machine learning approaches, where the first stage, so in here, we just inputted the surface temperature images to the network, and it tried to estimate the target mask. And on the right-hand side, we inputted the virtual waves that we extracted from the surface temperature images. And from the virtual waves, the trained network should find out what could be the initial temperature profiles. And you can see the defects closer to the surface. The surface is again represents the horizontal axis. Represents the surface. So the bottom, the top of these figures represents the surface. So defects closer to the surface has a better reconstruction or accuracy, but also some parts of the deeper defects could be also reconstructed, especially of the larger networks with a higher accuracy. Here you can see the overall quantitative test, where for each SNR values or noise levels with different SNRs, we evaluated the average mean square error of the reconstruction. And you can see the machine learning based methods are always better than the strictly model-based approaches. There are not too much difference between the hybrid end-to-end approaches, but there's an interesting phenomenon around 30 dB. The end-to-end approach, the end-to-end network, cannot improve anymore. But the reconstruction provided by the hybrid approach, so the one which utilizes the two-stage reconstruction process, still increases. Here you can see another example for the same phenomena. You can see the surface temperature measurements at 30 dB and 70 dB quality. And at the bottom, you can see the difference of these two images. On the right, you can see the vertical wave, the corresponding vertical wave images, and the difference again at the bottom. And you can see there is no difference between the 30 dB and 70 dB measurements. It's basically white noise, but there is a significant difference between the extracted vertical waves. So here it seems like the vertical wave reconstruction provides more information to the neural network. It can extract more information if the quality of the images increases, so if the noise decreases. Okay, you can ask now, okay, we trained a network on simulated data only, very nice, and it works on simulated data. But who cares? Because we want to apply this on real world data, right? So what we did, we trained the network on simulated data only, and then in order to validate our methods on real world data, we asked the team of Günther Meyer and also Gregor Tümmerer to make some real world measurements at FH Wales. And they made a test specimen, which includes two steel rods embedded into epoxy. They heated up these steel rods by induction and measured the temperature evolution in time by an infrared camera. And we got the infrared camera images, so the surface temperature images about this measurement, about this specimen. And then we applied our reconstruction techniques. The first one that you can see here is a strictly model-based reconstruction where the two steel rods are reconstructed with the vertical wave technique, and also in the second stage, instead of applying machine learning algorithms, we apply the FSAFT, the frequency domain synthetic aperture focusing technique. So no machine learning were applied here. The ground truth position of the steel rods are indicated by a blue, and the reconstruction is indicated by red. And you can see as we go deeper inside the material, the reconstruction degrades. And even by changing the thresholding, the threshold value, we could not separate the two steel rods at the deepest part of the test specimen. And this even gets worse if we change the initial assumption. So if we rotate a little bit by 25 degrees, if we rotate the test specimen, this gets much worse. Okay, in this image you can see the machine learning approach where we did not utilize the two-stage reconstruction. So immediately from the surface temperature data, we try to estimate the initial temperature profiles by using a trained neural network. And you can see the reconstruction is much better now. We have some artifacts at the deepest part of the test specimen, but it's not so apparent that we have in the previous reconstruction technique. Also, if we rotate the test specimen a little bit, the accuracy degrades, but still the two steel rods can be clearly seen. And this is the hybrid approach. So the last one, this one is the hybrid approach, where in the first stage we applied model-based algorithms that we combined in the second stage with a trained neural network, with a trained UNet. And you can see the volume of the steel rods are better estimated, and also deeper inside the material, we have a good estimation of the two steel rods. This estimation degrades and artifacts appears if we rotate the test specimen, but still the two steel rods and the estimation is much better than it would be with strictly model-based approaches. Okay, and before I would conclude the talk, just let me give some examples about, or let me give some ideas about our future plans. So I have two master students who are working on each stage of the algorithm. In the first stage, Gergő Gallagher is working on to apply deep neural network in the first stage. So instead of applying model-based approaches in the first stage, we can utilize some deep neural networks to improve the reconstruction there. And also he's working on unfolding iterative solvers. So in the first stage, we used ADMM. This is a numerical solver to solve the sparse signal recovery. But this could be unfolded into iterative, the iterations in the ADMM can be unfolded into neural networks or neural network architectures like the VistaNet. And Gergő Gallagher, who is also with us now, he's also joined us today. He is working on the first stage. And my other student, István Sagyabó, is also working on the second stage, where he's trying to improve the reconstruction accuracy by extending the training data with other type of defects, non-uniform defects, non-square defects, and also adding other types of noise like Poisson noise. Here you can see some examples about the new data samples. So in the future plans, we want to apply the network on not just square shape defects, but on defects with ellipses and also line type defects. So not just point defects, but line type defects could be good to detect. And this is an example to the VistaNet. This VistaNet is coming from a recent paper from 2021, which is applied to CT reconstruction. So the application, the fundamentals of this application in this paper is very similar to what we want to do in case of thermography. So this could be a good direction to go in the future. And yeah, that's my final slide. So we have many papers. Fortunately, we could publish by these results. We have 3 conference papers, and also we could publish 3 journal papers in this topic. One of them is in the Journal of Applied Physics, and the other is in the IEEE Signal Processing magazine. So yeah, but hopefully there will be more also with our future plans. So thank you very much for your attention, and yeah, I am happy to answer to your questions.
Thank you very much indeed, Peter, for this great talk, great overview on the techniques. Thanks a lot.